study of the energy distribution in an intrinsically nonlinear system. Our intrinsically nonlinear system is a couple of pendulums connected by a spring. A pair of pendulums connected by a spring. We determine the Hamiltonian, the Lagrangian, the equation of motion, and the energy distribution of the system. Let me show you here today, first now, the case of a small oscillation with theta 1, theta 2 are much smaller than 1. We know the solution for this problem, very interesting problem. The solutions of the system solution it contains will be given by the superposition of two modes of oscillation. The first mode of oscillation is the one in which the evolution theta 1 and theta 2 are in phase. So there is like there is no spring. The spring is like there is no energy in the spring. And the other mode of oscillation in which in the both angles are out of phase. Let me show you our numerical results. Yes, this is look, this is the plot of theta 1 and theta 2 as a function of time in the first mode of oscillation. The evolution, yes, in which the initial condition are theta 1 at time equals 0 equal theta 2 at time equals 0 equal 1, and the velocity of both pendulums at time equals 0 equals 0. So they are in phase, and let me show you the energy. The energy of the pendulum will be equal, and the energy of the coupling will be 0. It's like there is no coupling between the pendulums. In the second mode of oscillations, let me show you here. This is theta 1 as a function of time, and this is theta 2 as a function of time. The initial conditions are theta 1 at time equals 0 equal 1, theta 2 at time equals 0 is equal to minus 1, and theta 1 dot is equal to theta 2 dot equals 0. So in this case, they are completely out of phase. And let me show you the energy. The energy is very interesting because this is the energy. Look, the energy of the first pendulum, the energy of the second pendulum, and the energy of the coupling. The magnitude, the amplitude, maximum amplitude of the energy of the coupling is larger than the maximum amplitude of the energy in any of the both pendulums. It's very important to tell you that the sums, the addition of these three energies will be constant in this case. And in all the cases I will show you in this video. Let's move on to this next case. I will try this. My idea here is today is to show you the evolution of the nonlinear case. In the nonlinear case, I will find this very nice case. The first, like a slinky, the evolution of theta 1 as function of time looks like a slinky, and theta 2 looks like a slinky as well. The initial conditions are slightly different than the previous case, the second mode oscillation. The initial condition are theta 1 at time equals 0, theta 2 equals minus 2, 1, but theta 1 dot at 0 is equal to minus 0.05, and theta 2 dot equals 0. So they change, slightly change in the initial condition of the velocity produces an interesting case here. And also the energy, the total energy of the system remains constant and equal to 2.3368. The parameter beta is equal 1, and the parameter alpha in all these experiments are equal 1. Next, let me go on to here. This is the energy of the first pendulum as a function of time. This is the energy of the second pendulum as a function of time, and the coupling energy again. Is the maximum amplitude of the coupling energy is larger than the maximum amplitude energy in the pendulums. Yeah. Let me try. This is the reference, very important. If you would like to look, you can find it and read it. Very interesting paper. Here is the phase diagram for the first pendulum. This is the velocity of the first pendulum, theta 1 dot. This is theta 1 dot, the amplitude position. This is the phase diagram for the second pendulum. This is the theta 2 dot, and this is theta 2. Let's take another experiment. This is another experiment, another variation for the energy as a function for theta 1, sorry, as a function of time, and theta 2 as a function of time. In this case, the energy is 2.36. In the previous was 2.33. In this is 2.3668. Beta is again 1, and the initial condition is 1 minus 1, and I change the initial velocities for theta 1 dot at 0.15, and theta 2 at 0, theta 2 dot equals to 0.20. And this is the energy of the first pendulum, the energy of the second pendulum, again the coupling energy. Yeah? 0.20, look, 0.20. Let me show you here the beautiful phase diagram, lovely phase diagram. Look appearing here for the first pendulum and the phase diagram for the second pendulum. This is very important in this problem. The energy is constant. This is Hamiltonian system, non-linear Hamiltonian system, in which there is an exchange of energy between the pendulums, and there is a coupling because the spring produces a coupling between the pendulums. In the next case, this is 0.20 and the energy is 2.3668, beta equal 1. I change the initial position of the initial velocity of the second pendulum for 0.21. In the previous was 0.20, and this is the variation of the evolution of the angle theta 1 as function of time, and the evolution of the angle theta 2 as function of time for beta equal 1. And this, the energy, look, the energy again, the energy of the coupling is very large. The amplitude or the maximum amplitude of the energy of coupling is larger than, well, almost, in any case, is increasing. Look, the energy of the first and the second pendulum is increasing. And this is the case, beta equal 1 again. This is, now look, the phase diagram for the first pendulum and the phase diagram for the second pendulum. Let's move on to another case. This is, in this case, is very interesting because the initial velocity of both pendulums are 0, beta equal 1, the energy is smaller, 1.4765, but the initial conditions are for theta 1 0 equal to 1.575, and theta 2 at 0 equal 1. So this is a interesting evolution. Yeah, very order, or almost like a sine function. And look, the energy, the behavior of the energy is very interesting. Look, where the energy of the first pendulum is minimum, the energy of the second pendulum is maximum, and vice versa. And this is the coupling. Look, look, the coupling energy in this case is very small, very small. This is very interesting result, because in the previous cases the energy of the coupling was very large. Look, was large, and in this case the energy of the coupling is very small because the velocity, initial velocity, was 0. And let me show you the beautiful phase diagram for the first pendulum and a lovely for the phase diagram for the second pendulum. Now, let's show you this fascinating result. This is theta 1 function of time, this is theta 2 function of time. In this case, the energy is 1.6786, but beta is equal to 4. So, in this case, the elastic force is 4 times larger than the gravity, than the wave. The initial conditions are equal to the previous case. The previous case, look, was with this 1.575, theta 2 equals 1, and this is the solution, and this here is our new solution, very orderly, well, lovely, and we may assume that the coupling, the energy of the coupling will be smaller. Yes, look, here the energy of the first pendulum is between 0 and 2, the energy of the second pendulum is 0 and 2, but the energy of the coupling will be 0 to 0.5. So this is our, let me show you finally the amazing phase diagram for the first pendulum. Look, the evolution and the amazing phase diagram for the second pendulum. These are the solutions and the using, by the way, I wrote a code using MATLAB, which is available. Also, is available this